All right, so we're going to talk in section 13.5 about chain rules. And chain rules also will lead us into a nice way of doing implicit differentiation. That's a little easier than what you've learned to do in the past. All right, so for single variable functions, so we have y equals some function of x, and x is some function of t. The chain rule tells us, just as a reminder, that dy dt equals dy dx dx dt. So this is our single variable chain rule. For multivariable functions, just like we have several partial derivatives, we have several chain rules. The chain rule, the first case that we're going to talk about comes from, actually is an extension of what we did with differentials. I said that we use differentials to define differentiability. This first case comes from the idea of using a differential. I'm going to call this case 1 for our chain rules. So for case 1, we're going to have z as some function of x and y. And x and y are each functions of t. X g of t and y is some h of t. So we could think of this as parametric equations for x and y, and t is our parameter. So z implicitly or indirectly is a function of t. So z is in. Now what we do for our first chain rule is if we think of our total differential, and we think of in our total differential we had terms that had dx and dy. When we think of x and y varying with time, and we take the limit as the change in time gets very, very small, and we can say that dz dt is dz dx, partial of z with respect to x, times dx dt, plus the partial of z with respect to y, times dy dt. And this comes straight from the total differential, but we think of x and y varying with time, and we let the time increment get very, very small. We take the limit. So this is our first chain rule. And our assumptions here are that z, g, and h are all differentiable. The first partials are continuous. Z being differential implies that f sub x and f sub y are continuous. So these are our assumptions for this chain rule. And again, this follows directly from what we talked about with differentials. Pretty straightforward, pretty not really groundbreaking in terms of what we do, how we calculate these. Now, if x and y vary as a function of two variables or more variables, then we have additional chain rules. So let's look at those cases.
So in case 1, you would have to take your partial derivatives and take your differentials. Like, where are you getting, what is dz dy? Is that Is that just the derivative of,
That's the partial derivative of z of our function with respect to y.
and then,
dy dt is the derivative of this function with respect to time. So you don't have to think about it in terms of differentials. This formula, this equation, comes from what we did with differentials. So all we're doing here is taking the partial of z with respect to x, multiplying it by the derivative of x with respect to t, and adding the partial of z with respect to y times the derivative of y with respect to t. So it's just calculating derivatives, multiplying and adding is really what we're doing. So if we have g or x and y a function of more than one variable, then we have our case 2. We're going to say that z is some function of x and y, that x is a function of s and t. So x is a function of two variables, and y is also some function of s and t. So z is indirectly a function of s and t. And we have several partial derivatives that we can find. We want the partial of z with respect to s and the partial of z with respect to t. So what we're going to do to find these partial derivatives is we're going to apply case 1 to each of these separately. So apply case 1 to dz ds and apply case 1 to dz dt. So we're going to say that dz ds is the partial of z with respect to x times dx, the partial of x with respect to s, plus the partial of z with respect to y times the partial of y with respect to x. So that's applying case 1 to this partial derivative. And then we apply case 1 to this partial derivative. So we say the partial of z with respect to time, or t, doesn't have to be time, is dz dx. Partial of z with respect to x times the partial of x with respect to time, or t, plus dz dy partial of z with respect to y times the partial of y with respect to t. So that's just applying case 1 of the chain rule to this partial derivative. Yes?
You're solving the non-partial.
Well, in this particular case, our final result would be a partial derivative because z is varying with respect to s and with respect to t. Okay? And when we apply a chain rule where we have our function varying with respect to several other variables, we want to express our final answer in terms of the independent variables. And I'll write down here what we mean. Z is the dependent variable. It's the one that's changing as the other things are changing. X and Y in this case are intermediate variables. They're kind of between S and T and Z. And S and T are independent variables. So when we have a chain rule, in this case, we want to express our final answers in terms of the independent variables. So z might be expressed in terms of x and y, but when we take our partial derivative with respect to s or with respect to t, we want to express our answer in terms of s and t. Those are our independent variables. We don't want to express it in terms of the intermediate variables. So questions on kind of the development here. Again, chain rule not really complicated, not really that different from the single variable chain rule. One thing that can help to remember how to do these partial derivatives is a tree diagram. So let me draw a tree diagram really quickly. They're not difficult to remember, but if it's helpful, you can think this little visual. So if I have z, and z is a function of x and y, and x and y are functions of s and t. To go down a branch, we're taking a partial derivative along a branch, dz dx. And if I go down this branch, this is going to be the partial of x with respect to s. And this branch would be the partial of x with respect to t. Same thing on this side. So to find the partial of z with respect to s, we just follow along the tree diagram, multiply along each branch, and then add the results. So the partial of z with respect to x times the partial of x with respect to s, partial of z with respect to y times the partial of y with respect to s, and then add those together. And then in terms of our variables, our dependent variable is on the top. Our intermediate variables are here in the middle. And our independent variables are here at the bottom. So if it helps you to remember how to put together these chain rules, a tree diagram can be helpful. And if this last branch just had one independent variable, then it's, rather than a partial derivative here, we just have a regular derivative. If, for example, if x just varied with s and not another variable, we'd have just a normal derivative on that last branch. So questions on chain rules. Chain rule fairly mechanical, not really a complicated idea. If we have functions of more than two variables, the same pattern holds. So we could talk about a general case where we have a function of a certain number of variables, and each of those intermediate variables is a function of a certain other number of variables. The same pattern holds for functions of 3 variables, 4 variables, and when our intermediate variables are functions of 3 variables, 4 variables, same exact pattern holds. Any questions before we go on? So I want to talk about one more application of the chain rule using implicit to get us a way to do implicit differentiation a little more easily than what we've done in the past. And then depending on our time, we'll do an example or two. All right. So implicit differentiation. So a lot of times when we have some kind of complicated function, the functional dependence of one variable with respect to another is kind of hard to get to. But using partial derivatives, we can simplify that process. So let's say we have some function of x and y, and I'm using capital F here, and this function equals 0. And we're going to assume that y is an implicit function of x. So we're going to say that y equals f of x. Somehow. We don't necessarily have an explicit functional dependence that we can get to, but we're saying that y does vary as x varies. So I'm going to substitute f of x in here for y. So I'm going to say we have f of capital F of x and f of x equals 0. And I'm going to apply the chain rule to this. Take the derivative. So I'm going to say that the derivative of 0 is still going to be 0. So I'm going to say that the partial of big F with respect to x times the derivative of x with respect to x plus the partial of big F with respect to y times dy dx equals 0. Well, what's dx dx? 1. And so I can rearrange this, and I can say that dy, I'm going to solve for dy dx equals minus the partial of f with respect to x divided by the partial of f with respect to y. And we usually write this as minus f sub x over f sub y. And of course we're assuming that f sub y is not equal to 0. So this gives us a way to find the derivative of y with respect to x by using partial derivatives. So if we have some kind of complicated relationship between x and y, x squared y plus 3y squared x minus 2xy squared equals 0, it's going to be hard to solve for y in terms of x and find our derivative. Or implicit differentiation can be difficult because then we have to take all of our derivatives and solve for dy dx. This gives us a really quick, straightforward way of doing this. And if we have our big capital F as a function of x, y, and z, more than 2 variables, and we say that z is implicitly a function of x and y, dz dx, the partial of z with respect to x, is minus f sub x over f sub z, and dz dy, oh, yes, this should be a z. dz dy is minus f sub y over f sub z. So we have some messy, complicated function, and we want the partial of z with respect to x. We can use these partial derivatives to find our derivatives. Questions? All right, let's look at a couple of examples of calculating with these. So let's find, we want to find the partial of w with respect to s, and the partial of w with respect to t, where w equals y cubed minus 3x squared y. X equals e to the s. Y equals e to the t. And we want this at s equals 0 and t equals 1. So we want to find these partial derivatives with respect to s and with respect to t. And x and y are functions of s and t at these particular values. So writing out our chain rule, dw, the partial of w with respect to s, is going to be what using our chain rule? dw partial of w with respect to x times partial of x with respect to s plus dw dy times the partial of y with respect to s. And dw dt, our partial with respect to t, is going to be similarly dw dx dt plus dw dy dt. So we need a bunch of partial derivatives to find our partials using the chain rule. So dw, let's find the partial of w with respect to x. What's that going to be?
Negative 6xy.
Minus 6xy. How about the partial of w with respect to y? 3y squared minus 3x squared. Let's find the partial of x with respect to s. What's that going to be? E to the s. Partial of x with respect to t. 0. And then let's calculate our other dy ds, the partial of y with respect to s. 0. And the partial of y with respect to t is going to be e to the t. So we have everything that we need here. A couple of the terms go away because we have these partials equal to 0. So we're just going to substitute some values in. See, dw des is going to be minus 6xy e to the s. And we know that x is e to the s and y is e to the t. So if I substitute those in, I get minus 6 e to the 2s plus t. And when I plug in s equals 0 and t equals 1, my partial is going to be minus 6e. So I'm just plugging these two values in here. So this is what I meant when I talked about expressing our partial derivative in terms of the independent variables. I wouldn't want to leave it like this. I would want to write it like this. 2s, yes. Because I get an e to the s from x. And then our partial of w with respect to t. I'm just going to put in my values. I get 3 y squared minus 3x squared times e to the t. And if I write this in terms of my independent variables, I get 3 e to the t times e to the 2t minus e to the 2s. And when I substitute in s equals 0 and t equals 1, I get 3e times e squared minus 1. So again, when I get to my answer, I want my independent variables in my answer. If I weren't plugging in values, this would be my final answer for just an expression for dw. So, partial derivatives, they're interesting. They open up a lot of doors, but there's a lot of calculation in partial derivatives, especially when we get complicated functional dependence. Questions? All right, let's look at an implicit differentiation example, and then we'll be done. So let's say we have e to the xy plus xy equals 0. I'm sorry, I don't want xy, I want e to the xz. So in this equation, z is implicitly a function of x and y.
Does it require just one z in the equation so you can theoretically pull it out into one equation? Is that why it's implicitly a function?
Well, we could, even if there were more than one z in there, that we could say that in some way there's some relationship between z and x and y.
Okay.
Even if we can't necessarily solve it and find it, there's some relationship there. If x and y change, z is going to change also. So we can say z is an implicit function of x and y. It depends on x and y somehow. We want to find dz. We want to find the partial of z with respect to x and the partial of z with respect to y. Now with this particular function, it would be extremely difficult. It would be difficult to solve for z in terms of x and y. We could use implicit differentiation the way we've known how to do it before, where we take the derivatives and write in our dz dx's and dz dy's and solve for the derivative with respect to x or the derivative with respect to y. Again, it could be very difficult. But we just came up with a method to say that dz dx, the partial of z with respect to x, is minus f sub x over f sub z, and dz dy is minus f sub y over f sub z, where f is e to the xz plus xy. So this gives us a really easy way to calculate this. So we just need to calculate 3 partial derivatives and form our quotients. So our partial of f with respect to x is going to be what? Z e to the xz plus y. Our partial of big F with respect to y, just x, right? And our partial of f with respect to z, x e to the xz. And now I can just form my quotients. So dz dx, partial of z with respect to x, is just going to be minus z e to the x y plus y over x e to the xz. And dz dy, the partial of z with respect to x, yeah, that's supposed to be a z. This should be, yes. Why do I not want to write that z today? Dz dy, the partial of z with respect to y, is minus x over x e to the xz, which we can simplify just 1 over e to the xz. Quick, simple, much faster, much easier than the method that we would have used for implicit differentiation in the past.
So does the negative, it's not in front, or does it like when you have to put parentheses around anything? Like for the first one, you have the negative out in front of
I could think of it as this. But it's just changing the sign of the whole thing. I could think of this one as -1 over this. All right, any other questions? Okay. Well, now we know how to use chain rules for partial derivatives. Homework's page 929. All right, there you go.